This is the OFI testing equipment HTHP filter press, commonly called a high temperature, high pressure filter press. And this particular model is a field portable unit that has 175 mils cell capacity. Actually, the cell capacity up to the lip of the O-ring is about 170 mils, and when you leave room for the fluid expansion, it's closer to 140 mils of actual fluid sample that you're running the test on. I am presently preheating the heating jacket, and normally you do this to 10 degrees Fahrenheit or 6 degrees centigrade above your target test temperature. In this particular case, we're heating up to 250 degrees Fahrenheit. I have a thermometer in my heating jacket. It tells me that I'm at the 250. The light, it comes on and goes off as the heaters turn on and off. But when the light comes on, I am at my target set temperature. And that temperature is set by this knob. The scale on the front of the thermostat is just 1 to 10. So most people put a mark slot. In this particular case, I've marked where 200 Fahrenheit is, and you can mark 250 and so on and so forth. The maximum temperature that you go up to with the 175 mil high temp filter press is 350 degrees Fahrenheit. The reason for that is the fluid expansion. You normally leave a ½ an inch fluid expansion in the cell, and if you go above 350, you have to leave an inch or an inch and a half, and you just don't have enough fluid sample to get a meaningful test. So above 350 degrees Fahrenheit, you really need to use a 500 mil HTHP filter press. So that basically is the heat up. And while it is heating up, you check the O-rings on your valve stems. There is an O-ring on either end, and also the O-ring in the cell body. There's an O-ring in a groove here, and there is an O-ring that goes in the groove of the cell cap here. That O-ring is our part number 17013 for the cell body and cell cap. That is a Buna N synthetic rubber that's good to about 300 degrees Fahrenheit. We also have Viton O-rings, part number 170-13-3, for temperatures a little bit above 300 degrees Fahrenheit. However, we recommend that 300 degrees F and above, you change O-rings after each test. The reason being is these O-rings get what we call flat spotting or drift. They become deformed. In some cases, over a period of time, you get nicks that develop in the O-ring, and they won't provide as good a seal. In some cases, you can end up with a failure. So, once again, above 300 degrees Fahrenheit, we recommend you change O-rings after each test. The valve stems are used to pressurize and depressurize the cell. You hook your pressuring assemblies up to the valve stem. I have here the inlet valve stem, and I have tightened it already. You want that to be good and snug. When you tighten it as far as it will go, it puts a metal-to-metal seal, and that O-ring also seals, and it seals the cell off so that nothing can come in or out of the cell. And so since this is the inlet side, and I'm going to invert it to fill the cell, I will close that off so that mud can't go through the valve stem and get out on the table. So in some cases, the 2,000 mil cells have a cap on the other end, and in that event you line your arrows up on the cap and the cell body and do your set screws, tighten them in place, and then tighten the valve stem. This is a standard 1500 mil or 1500 psi cell assembly that we send out with the stock filter press, number 17000 for 115 volts and 17001 for 230 volts. And the 1500 psi cell has only a single cap. The other end is sealed. Sometimes you hear this referred to as a single-ended cell. Still has two ends, but it is a single cap cell. So I'm going to The next thing I want to do, since I have sealed off the bottom of the cell, is I want to pour my mud sample into the cell. This mud sample is a water-based fluid supplied to us by one of our customers, which is one of the largest mud service companies in the world. This was used in South Texas on a rig, and it has a mud density of about 12 pounds per gallon. When I pour this into the cell, I want to leave that half an inch that I was talking about for the fluid to expand, or 13 millimeters for the metric folks. And that space is the space above the liquid and below the O-ring gap, or the O-ring groove. The reason for that is that as the fluid inside heats up, the fluid is going to expand, and if I don't allow room for that expansion, I can blow the cell cap off of the cell. So that's a nasty mess that we would rather not have to deal with. So I'm going to pour my fluid into the cell very carefully. You want to be careful not to get the fluid into the O-ring groove or on the O-ring, because if you do, you can't get a good seal and you'll lose pressure when you go to pressurize the cell. So I've left a half an inch for fluid expansion. I have not contaminated my O-ring groove, so the next thing I want to do is place a circle of Wattman number 50 filter paper on top of my O-ring. Very carefully. Make sure that it is seated all the way down and is not crimped or anything like that. This Wattman 50 paper has a pore retention, average pore retention of 2.7 microns. And that means that a particle 1/3 the size of that theoretically can seal it, the rule of thirds. So if you get 3 1 millimeter or 1 micron particles come through at the same time, theoretically they can seal this particular cell assembly. So I've got my filter medium in place. The next thing I want to do is very carefully install the cell cap into the cell body. There are arrows on the cell cap, and I want to line the arrow on the cell cap, which hopefully you can see, with the arrow, yeah, maybe there, with arrow on the cell body. Once these are lined up, then I know that the set screws will mate with the set screw holes. I want to install my valve stem, and I don't want to tighten it because I want air to be able to come back out, because when I push this in, I'm going to be pushing against a vacuum. I also want to be careful to put a light coat of never seize or stopcock grease on the cell O-ring. That will greatly facilitate removing the cell cap later on. This heat, it will expand the stainless steel. And a lot of cells, in fact most cell caps that you see that have been used for some time, have hammer marks on them where they've tried to beat the cell cap out of the cell. If you put a little bit of grease on there and you use the cell cap removal tool, which is one of the handiest devices that we sell, you'll find that cell cap removal is very easily done. So what I'm going to do is line the arrows up. I have my filter medium in place. I then gently push it down. That went in pretty easily. And I now get my Allen wrench and I will tighten my set screws. I want to tighten my set screws. I can quickly tighten as I try to facilitate this as much as possible. And initially, just snug it up and do every other one. And the main thing with these set screws, though, is you want to make sure that they're all tight, all 6 of them. You don't want to have one set screw that's jutting out past the wall of the cell. We frequently get high temp filter press jackets in with the cell that's welded inside of the jacket, And the reason for that is that someone did not thoroughly tighten all of the set screws, and one or more of them was sticking out, and when the heat got to the cell, it expanded, and making the cell body extremely difficult, if not impossible, to get out of the heating jacket. Sometimes there's nothing we can do with it either. So just be careful that these are all tight. And one way to do that is that if you start off at a known place. This says O-Fight. I'm going to tighten this one first. Then I'm going to go around to the next one and snug it up thusly, and to the next one, and I'm going to snug it up. Drop the Allen wrench. Okay, and snug that one up. That one is tight, and that one is tight, and I'm back to the original one that says O-Fight. So all of my set screws are snug, tight, and in place. However, my valve stem is still open because of ease of putting it in place. So now what I want to do is tighten the valve stem, and I do that loose tighten, and then tighten it with the crescent wrench. So now I'm in good shape. I've got a cell, the cap is sealed, the valve stems are sealed, there's nothing that comes in or out of this cell. So I want to invert the cell. Since my filter medium is here, I'm going to be filtering down and place the cell in the heating jacket. I want to transfer the thermometer to my heating jacket. But first, I want to rotate the cell until it seats. And you hear it right there. There is a pin in the bottom, and that pin mates with the holes in the cell body. And now, what that pin does is it prevents the rotation of the cell, so I can tighten and loosen the valve stems at will. I want to take my thermometer and remove it from the heating jacket and place it in the cell wall, thermocouple hole. The temperature right now is reading about 150. It was reading at 250. So I have a cool cell that I'm placing in the heating jacket, and I'm going to have to allow an hour for that heat to convey itself from the heating jacket into the cell. So in the meantime, I can do some things. I can connect my pressuring assemblies. My top pressuring assembly, both of these operate off of CO2 bulbs, and I will place my top pressure assembly in place. I want to make sure that my T-screw is not supplying any pressure to the diaphragm so that no pressure can get into the cell. I want to hold this in place with the retainer pin. And sometimes these things, you have to line up the groove like so. And I want to turn this like so. And then there is a cotter pin on the end, so I want to put that in place so that the lanyard will stay in place, and therefore the retainer pin can't blow off of the pressuring assembly and off of the needle valve. I do the same thing with the back pressure receiver on the bottom. I have the appropriate lanyard pin as well. I place this on the valve stem, put it in place. I attach the cotter pin to the lanyard and being very careful not to burn myself because this heating jacket is hot, about 250 degrees Fahrenheit. So now I have the top and the bottom pressure assembly in place. Before I put a CO2 bulb, before I do anything, I want to make sure that this is loose, is turned counterclockwise so that it won't supply any pressure to the assembly. And making sure this is loose, and also the same thing with the back pressure receiver. I have no pressure can get in once I puncture the CO2 bulb. Additionally, I want to make sure that my bleeder valves are closed. They need to be clockwise, tight. If it's loose, then pressure can come out here. So I tighten that one. I make sure that my back pressure receiver ball valve is tight. I make sure my bleeder valve is tight here, which this is a push-pull type affair, this red bulb, so when it's pushed in all the way, that will not allow pressure to come by. The safety bleeder valve here and here serve a dual function. They prevent us from putting too much pressure into the cell. Some of these big nitrogen tanks have 3,000 psi, so these are set to blow off at about 190 psi. Additionally, they allow us to bleed off pressure from the regulator to the valve stem at the end of the test, and I will show that when we get to that point. So basically, what we've done now is we're ready to hit this with pressure and install our CO2 bulbs, etc., etc. These CO2 bulbs are little pressure vessels. They have anywhere from 900 to 1,000 psi inside. And being small, they're a very portable pressure source, which is why we use them on these filter press units. We use them on a high temp unit as well as on a field unit. The bulb goes in the barrel, and we install the barrel in place without tightening it down too much. When we tighten it down, we puncture the CO2 bulb. I could puncture it now, but I'll do it all at the same time to show better how this is done. These threads are very coarse, so sometimes they're a little difficult to get on. So we've got all of our bleeder valves released or tightened down. Everything is in good shape. So this is a closed pressure system that we have right now. The API recommends or suggests, and most people do, that when you run a high pressure filter press test, that you're running a 500 psi differential. That means that you have 500 psi on top more than you have on the bottom. The bottom really dictates, the bottom or the back pressure really dictates the pressure that you use. And that is dictated by the temperature that you go to. When we go above the boiling point of water, the boiling point of water is 212 degrees Fahrenheit or 100 degrees centigrade. When we exceed that, the liquid, if it's water, and water-based fluid is typically what we use, that will turn to steam. So to prevent our base phase water from turning to steam, we elevate the pressure. At 250 degrees Fahrenheit, which we're at now, the vapor pressure is about 30 psi. So I've got to be in excess of 30 psi, and we typically put 100 psi on the bottom to keep it from turning to steam, to keep our filtrate that we collect from turning to steam. If we're going to put 100 on the bottom, then we're going to put 600 on top, and that is our 500 psi differential pressure. So what we're going to do is we're going to puncture the pin on top, tighten it down, and I'm going to run this up. Since our back pressure is going to be 100 psi, we initially start off with the same on top as we do on the bottom. So I'm going to run this up to about 100 psi. Now the valve stem on the top and the bottom are closed. I'm going to do the same thing on the bottom. I'm going to tighten the barrel down, and I'm going to tighten my regulator T-screw. That will apply pressure, and this is not pressurizing up. Maybe I didn't tighten this far enough. Sometimes you get a bad CO2 bulb that just doesn't puncture for whatever reason. So I'm going to try another one. That one is a used one. Okay. I don't know why, but it just sometimes they don't work. So you just have to get another one. And we're struggling with these threads here. I mentioned they are coarse. All right, so I will tighten this down, and we'll see what happens here. There we go. All right, I have 100 psi on the bottom. I have 100 psi on the top. But my fluid inside is cooking. It shows it's a little past about 210 right now, so we've just exceeded the boiling point. So I need to alleviate or let pressure go into the cell. I do that by loosening the valve stem about a quarter of a turn. So I will hold the base of the assembly to keep from, I can't hold the jacket because it's hot, and I turn that just a little bit, and that lets pressure 100 psi into the cell. And you have to constantly monitor the top pressure and the back pressure, make sure you don't have any leaks. So what I'm going to do now is sit here and let it cook for an hour. The hour heat up time is that so you get a heat transfer from the hot heating jacket into the cell body, and then consequently from the cell body into the fluid. We ran a number of tests where we put thermometers, thermocouples, in the fluid years ago, and we found that with this particular size filter press, after 30 to 45 minutes, on virtually 98% of the cases, the fluid inside the cell was at the target temperature. But it does take a while. So just because your thermometer says your fluid is at the temperature, what this thermometer says really is that the cell wall is at the temperature, but not necessarily the fluid inside. So that's why we recommend 1 hour heat up time, but you don't want to exceed that 1 hour heat up time because the fluid consistency can change if you sit there and let it cook for too long. And we found that that is very true. That's also per API specifications. So what I'm going to do is turn this off rather than watch it cook for an hour, and then I'll come back and we'll run the test.